Hello, everyone. Welcome to another problem session. And we are on magnetism now. These are kind of standard problems in magnetism. So last time we talked about the magnetic force on a moving charge q with velocity v in a magnetic field denoted as B. Okay, and this is just Q V cross B. So this is we're writing in SI units. If you have some other units of the charge, you will write it a little bit differently, but we're going to write it like that. Okay, so SI units or also MKS units. Okay, now we're gonna answer questions about the not just charge, but we know that electric current is a drifting of charges, right? So if a wire is carrying a current, then it's got the drifting charges. And so if I place that wire in a magnetic field, then each one of those drifting charges will experience a magnetic force, and that should that force should become the force on the entire wire, right? So add up. So that's the basic idea. So that's the question A. So there will be so for A, the answer will be very similar to that, and I'm going to derive that answer. So if magnetic force on, say, length L of the wire over the length L of the wire, that will just be L times the current. Current will be in the direction of the moving of the charges. I know the electrons are moving, and so this is just a kind of electron moving down and this fake positive charge moving up. That's how we kind of use the current, right? And cross B. So this will be almost like the same thing, and we're going to see how this becomes. And it's also a cross product. So this is a cross product, and you should review the cross product in vectors. I don't have time to review it. Over here, the question is, okay, now we have know how to do force on a segment. Now if I have a full kind of a loop of wire that's in the magnetic field, there's other parts of the circuit I'm not talking about, just this loop part. In this loop part, it can rotate about this post. Then what will be the magnetic field if, say, this is a height h and this is width w? Okay, so what can we say about the torque about this axis? Because there will be force, and then there will be if the force is away from the axis in right direction, it can cause the torque on the loop, right? The entire loop. So that's also a good question, and a lot of students struggle with this derivation. So let's unless you want to go ahead and do the derivation and then come back to the answers. So the answer here will be the torque here. We can write down the torque as a magnitude. We already know the axis. Axis is that way, so the torque is pointed along the axis. So the torque along the axis is just going to be I'm going to write the positive value, and it's going to be almost like that. So it's going to be current times, we can define an area vector cross B. It's going to be like this, almost like that, where L because the current is changing direction here, see this way, and over here is that way, over here is that way, over here is that way. So we don't write this in this way. Similarly, over here you could write just I, and L is much better to write like that than write Li. L is the direction in which the current is flowing, or the direction of in which the wire is oriented in space. Okay, so this is both ways to write it, and we cannot write like that. Now this quantity here, I times A, or vector A, we can talk about how do you make an area a vector. Vector A is called magnetic dipole moment of the loop, this whole loop. So this depends on the area that's the loop occupies in the magnetic field. So magnetic field is everywhere. So these are the magnetic field. Magnetic field is everywhere. So these are the B lines. We will have more discussion on magnetic field later, but suppose we have magnetic field like that. That means we have some kind of north pole here and some kind of south pole here. And we're doing this experiment right in the middle of that. Okay. And we're going to also assume that the B is uniform. So we're going to assume B uniform. We're going to also assume B uniform here. So it's the same. So this over here is like a north pole is, you might say north pole is here and south pole is that way. And we're doing that part of the wire is between north pole and south pole. The direction between the wire and the magnetic field lines is angle theta. Okay, let's do this out. Okay, so to do A, notice that current I is equal to current density times the this wire we're looking at, this some kind of area of cross section A. So this is the wire. This is wire of length L we're looking at. And so current that's carrying in this wire is related to current density times the area of cross section. Okay, and current density is conduction electron density. How many conduction electrons? Ne is number of electrons, conduction electrons per meter cube, per volume. Okay, so we're talking about SI units, so we can just give meter cube. So Ne times charge of the electrons, E, and this is the drift velocity, not real velocity, but it is overall velocity. So we're just going to do V sub D, and so that's times area A. So that's, see, this is where the velocity is. So let's write this whole thing out a little bit. Ne times E times area of cross section. This is some constant of this geometry and some constant properties of the material. So these are constants times V sub D. So if I think of this as if you remember, I got to think in a vector, right? So these are, if you look at how many charges are there, you can just think of this as in like that. Then I need to get the Q. You will see Ne times area of cross section times L is going to be Q in this whole thing, in this at length L. So we can convert this as a times E. That's going to be QL. This is the number of conduction electrons and charge, but this gives QL. So I can see this will be QL over L times VD. We're just gonna just call this V. And so if I want, these are scalar, these are scalar. So this where the vector will be. So if I say I vector is QL over L V. So looking at this, magnetic force on the length L of the wire, the entire length of the wire, will be, you can see this is QV, so it's 1 over so QV is IL, so we have a QL V cross B, so that's going to be formula from thinking of that as charge, just a point charge, and so QL becomes IL. We can write this I vector L either way, same thing, cross B. So this would be on length L, and the question is the per unit length, so the FM L over L will simply be take I as a vector cross B. So this is the answer we're looking for, and if you can think of this as B was not uniform, if there was more B on this area, then that is then I'll have to divide this whole length into different regions. I have to integrate and things like that, right? So if you're non-uniform, you can generalize. So F ML, this will be vector, will be just it will be same current everywhere, right? So you'll have a DL, some small element here, DL cross B, and I have to integrate over this length. So this is like a formal. So you'll have to do this integral if you want to do a non-uniform B. This might depend on what point I am. So this point P at point P, and this at point P. So I'll have to set this up and do this integral. So it's going to be I will be same. You'll have a DL at some point P cross B at point P. I need to have a exact expression for this, and over length of the wire. So this is the general, but for our particular case, it's just simply this, or over, if you want to have a length L, how much force this segment of the wire will feel, that's going to be that much force. Okay, let's do B. Okay, so for B, notice that the force, you may remember the torque of a force is R cross that force. So R is from the axis, right? So if I have a beam, and if this is where my axis is pointed, and if the force is that way at that point, and if this angle is, say, theta, then I need to extend this. We extend this line of force, and from here we drop from the pivot point we drop a perpendicular to this, and so we need, this is the lever arm. So if this was like a distance L from there, then if this is theta, then that's theta, and so over here is L sine theta. So you'll have a torque here will be F L sine theta. When I work this out, we're going to have something like this here, right? So in each case, we got to figure that out. So let's look at over here. axis is this way, so let's call it this z-axis. And so this thing, and maybe this magnetic field is along the x-axis. And so this is when you look at, if the current is going that way, and so I need to you can x and the y is that way. This is this xy plane, right? Xy plane. So this thing is actually in the xy, this one, the way I've drawn is an xy plane. So if I look in xy plane, so this is the x, and this is where the b direction is, and this wire is in this direction, and this one we are calling phi, is in that direction. So let's call it that direction. Well, when I take this is I vector for this segment, I vector, and this is the b vector, and this is both of them in xy plane, which means it's going to be along the z-axis. When I take a cross product, I cross b, it's going to be you can see that if the b was pointed that way, it's going to be up. If the b was this way, okay, it's very easy to do it. So so if I do it like this, it's gonna, z-axis is coming out. Z-axis is coming out like that. We write like that, coming out. If b was this way, then it will be like that. But b is the opposite way, so the way the force will be is in the negative z-axis. Negative z-axis. That's where the force will be on this guy. So if you look at this guy, let me take a good pen. Okay, so if I look at this part of the wire, if I look at this, the force is force on this is in the negative z-axis, in that direction. I think let me take a little bit more. Yeah, it's in that direction. It's parallel to the axis, so it's not going to have any torque. So let's call this A, let's call this point B, let's call this point C, let's call it D. So A and B, this part of our no torque. Torque on A, B equal to 0. I do this way, you work out this way, this part will have force this way, this force this way. So this guy, again parallel to the axis of rotation, that's going to CD is also 0, and BC is right on the axis. BC is 0 on axis, so R perpendicular equal to 0. So this, and this is parallel to axis. Force parallel to axis, force parallel to axis. Those are the reasons for these guys to be 0. So only thing is we work out this. So what is the force on that? Well, let's draw a picture like this for that. So we have this is along the z-axis. This is current is parallel to the z-axis. So this is but the B is parallel to x-axis. So I is I k hat, and B is B. No need to draw it, actually. It turns out to be I hat. So I cross B will be K cross I is minus J hat. No, plus J hat. It's K cross I equals to K hat cross I hat. So I cross B So what do we get? We get tau dE, d to a. This one, the magnitude is the length of the wire. Actually, if we do the force on dA is along the j hat direction, and you have a I times B times this length of the wire. So that I times capital B times length of the wire, that's the force. So force is so let's now look at the xy axis. Force is along that direction. So if I draw it out here, so force is along that direction. Force is along that direction, while you can see that if I drop a normal to this y-axis, it's going to be that distance, and so we are looking, the distance is going to be cosine phi of the width. So the torque dA is IBL with cosine of phi. Okay, so this angle over here is phi. But often what we do is we don't do the normal. We do the we look at this as an area. You can look at BLW is an area, and we go to the current. Current is going this way, so we kind of wrap around the current, and we define an area vector coming out like that. If I go counterclockwise, the area vector will be coming out like that, which is also the normal direction for this area vector. Same direction as normal direction to the area vector. So this whole thing I can write, I write this thing as area. So I times A times B cosine phi. And if you do it like over here in the XY plane, if this is the y-axis, right, then this area vector, y-axis is in with respect to that, but the area vector is perpendicular to that, so it's going to be coming out like that. Area vector will be a little bit like that, not along that, but along that. And so that angle from between these this and this, that angle will be sine theta. So this will be, we can write down IAB cosine pi over 2 minus theta it's going to be minus theta, yeah, because on the other side. So it's going to be IAB sine theta, and this theta is the angle between normal direction and the B direction. So if I define a vector A as A times n hat chosen using right hand rule, and this right hand rule is if the current is going that way, then n hat is that way. If the current is going other way around, if the current is going that way, then n hat is pointed in the back that way. So if I define like this, then I can do torque vector is going to be I A cross B, and that will explain why I've got the sine theta. So this will be the torque on the entire loop, because over here was 0, over here was 0, over here was 0. So this is the only part that has torque on the loop. So this is the torque on the loop, and this is the area of the loop, but defined as a vector in this manner. So that's the answer for B. Just aside that this quantity IA models microscopic magnets, and it's called magnetic dipole moment of the loop. IA is called magnetic dipole moment of the current loop. And you got to remember that the direction is pointed in the direction of n hat in this fashion. So that you have to go through the whole IA. You have to remember IA, and you have to remember that if you go this way, then this is this direction in which a hat vector is pointed. The current is going this way. Okay, this actually we will use when we look at regular magnets, you know, how the regular magnets work, material magnets that you're familiar with, macroscopically what they are, how to take into account what force on a magnet will be. So look, we have been talking about force on a current, force on a charge, but we're avoiding talking about force on a real magnet. You know, that turns out to be very complicated actually. And the way we talk about force on a real magnet comes from modeling the real magnet as a magnetic dipole, as a current loop. And when we use the current loop, we know what to do with the current loop, like what we just did. So it's actually a little bit of going around rather than talking about real magnets and magnetic dipoles that way, which is very complicated system. We actually begin by looking at force on moving charges, and then from moving charges we go to force on currents or current cutting wires. And once we have learned this, we can actually then in a position to address what to do with real magnets. We can model them, and then we will use our understanding of magnetic effect on moving charges to study that. Okay, so that's it for now. I will see you in another video. Bye bye.